take a look at a model of a typical suspension bridge. You see here. This model consists of two main cables. The cables are anchored out here on the ends. They extend up over the tops of these two tall towers, and then they're draped across the main span in that characteristic curved shape. From the cables, you see that I have suspended a series of weights. They're equal weights, and they're all spaced an equal distance apart. So this constitutes a uniform loading on the cable. The shape of the cable, then, is a direct consequence of that loading. It's really a function of physics. The shape of the cable, mathematically speaking, is a parabola, and the parabola occurs specifically as a consequence of that loading. It's science, not aesthetics. Up at the tops of the towers, the cable makes a sharp bend, and as a direct consequence of that bend, all of the tension in the cable is transmitted downward into the towers. And so, in effect, the two towers are carrying the entire weight of the bridge and everything that's applied to that bridge in compression directly down through the towers. And that's why on the Brooklyn Bridge the towers are so massive. They're such robust granite structures. So the parabolic shape of the curve of the cable is caused by the uniform loading. What happens if the loading isn't uniform? What happens, for example, if a heavy vehicle like a train or a heavy truck is crossing the span? Well, when that heavy vehicle gets out here to mid-span, note what happens. Note that the parabolic shape of the cables has now become distorted into something very different. One of the characteristic features of a cable structure is that it changes its shape in response to changes in applied loading. Well, that's all well and good, but if this is a functional suspension bridge, we have a problem, because that sort of distortion in the cable also caused a significant downward deflection of the deck that the vehicles are driving across. So imagine if you're the occupant or driver of a vehicle that's moving from one side of the bridge to the other. When the vehicle's located here, the cable distorts into this shape. As it moves to this location, the cable distorts again, but into a different shape. By the time it gets out to midspan, it's distorted into yet another shape again. And all the while, the bridge is undulating and undergoing all these crazy deformations. Clearly, it's not practical as a functional structure. And that's why most suspension bridges, to include the Brooklyn Bridge, use a secondary structure called a stiffening truss, which is supported directly from the cable. And I do want to emphasize that the stiffening truss is not resting on the towers. Note that there's a space between the ends of the truss and the towers. It's entirely hanging from the cable. But now when I take this same heavy concentrated load of the vehicle crossing the bridge and we place it on the stiffening truss, we see that the shape of the cables didn't change at all. What the stiffening truss does is to distribute that heavy load out laterally so that all of these slender vertical wires, they're called suspenders, carry that load instead of just one or two suspenders, as you saw in the case of the unstiffened